Hi, everyone. This is the final segment of Lecture 2. In this segment, we're going to be talking about the motion of the objects we see in the sky and what that tells us about our situation in our system. So, I wanted to start by going through a few of the objects that we see when we look up into the sky. So, obviously, the first thing that comes to the mind is the sun. The sun is a glowing orb. It casts light over everything. When it's in the sky, it keeps us warm. We can feel its warmth on our skin. We also can see the moon. It's a similarly sized orb. It is slightly different in color. It does shine its own light, or so it would seem, but it's not nearly as bright as the sun. And then, of course, when we look up in the nighttime, we can see these many, many, many pinpoints of light, the stars in the sky. And you can also see that there are some diffuse structures as well, like this band here. And when we try to figure out what these things are and how we're situated in amongst them, our first clue comes from the fact that when we look at these objects in the sky for long periods of time, they seem to rotate in the sky. So, this is a time lapse video showing how the stars in our night sky rotate around apparently the North Pole, the North Celestial Pole, every night. And if you take an image and you let the exposure time go for a very long time, you can see that the stars essentially smear themselves out into these arcs, and these arcs are all centered around the northern pole. It turns out that the sun and the moon follow similar pathways. So the moon also rotates around the pole in the same way. Here it is moving like that. And then you'll see the sun following it as well. So every day, the sun and the moon follow a very similar pathway to the stars. Here comes the sun, and it will rise and travel up like that. So the fact that the stars and the moon and the sun all seem to travel in circles around us gave rise to the idea many millennia ago that the earth was the center of the universe. Everything that we could see appeared to move around us. This is called the geocentric theory, this geocentric frame of reference. So the idea is that earth is stationary right here, and around us is a sphere of stars that are essentially painted onto the night sky, and they orbit around us and they move around us and cause the spherical and they cause the circular motions that we see in the night sky when we observe them. Now, the sun's motion is similar to the stars, but it's not exactly like the stars. It turns out that when you look at the star at the same time every day, it's basically in the same place. But over the course of the year, the sun's position in the sky seems to change with respect to the stars. So this diagram is showing on this little part how the sun moves over time in a day. And that's this arc that we see familiarly every day. So at 6 o'clock, it starts here, and then every 10 minutes, it moves a little bit further up in the sky. But if you do the same experiment and observe the sun at the same time every day, you see that it ends up in different places throughout the year. Here's March 3rd, here's February 3rd, here's January 18th. So the location of the sun in the sky on any given day seems to change over the course of the year, which is different from the stars. The moon's orbit and path through the sky is also slightly different. So the moon seems to move rapidly across the stars. So on September 12th, on this example, it was over here. At the same time, on September 13th, it would be over here, and 14th and 15th, and it would eventually not even have risen yet on the 16th at this particular time from this particular location. There are also other stars or other objects in the sky that seem to behave differently from the vast majority of the other pinpoints. So in this image, I'm going to be showing the movement of several of these apparently wandering stars. So in these circles here, you can see that there are some stars that seem to be constant. They're not moving. And if you take an image of them every night, they appear to be in the same place. But this star seems to be wandering. It seems to be moving with respect to the others every so often. Here's another one over here that's doing the same thing. You can see that these two wanderers are not following the same pattern as the rest of the stars in the sky. And even millennia ago, the ancient Greeks realized that these stars were different, and they called them wanderers or planetae. So when you're trying to describe how things move in the sky, if you're using a geocentric point of view where everything's rotating around the Earth, you have to throw in some extra bells and whistles to describe this motion that's not quite the same for the planetae, which we'll call planets from here on out, and for the sun and for the moon. So, in order to describe this and this idea that everything is rotating around the Earth, you have to introduce these wiggles and changes in the pathway that the different objects take. So, you can see this object is moving around in essentially a cardioid shape, and it's having this little wiggle every so often. This one has a larger one. This object is moving in a different path. This one has a different one as well. So all of these tweaks have to be made to the geocentric model to describe the movements of every object in the sky and not just the distant stars. But it turns out that there's a simpler way to describe the motions of the planets and the sun and the moon in the sky. And it turns out that we can do this instead of by assuming that the Earth is the center of all of this and that everything orbits around the Earth, is that everything in the nearby vicinity orbits around our sun. It turns out that when you make this change, the math and the equations become a lot easier to describe the motion of our planets. It also turns out that you no longer need the complicated wiggles that we were showing in this previous image, in this previous video here, to describe exactly how the planets are moving around. Everything just moves around in a circle. The reason we see that the stars appear to be moving around the Earth in the sky is not because they are moving, it's because our Earth is rotating, and we can see this rotation, but we can't feel it, so it looks like everything else is moving instead of us. This video here has inverted that and has stabilized the stars in the sky and allowed the Earth to move in its stabilization, which shows the true way that our Earth moves around. We can explain why the planets move with respect to background stars in the heliocentric paradigm as well. So the idea is here's Earth, here's Mars. And as we look at Mars, it appears to be projected onto different parts of the sky. So these are the background stars that we see. They're very far away, so they don't appear to be moving. But as we move with respect to Mars, because we're nearby, we see it from slightly different points of view throughout our orbit. And this can cause the apparent changes in the apparent motion of the planet with respect to our own. So when we combine all of this information together, what we can find out is that our planet Earth orbits in what we call the solar system, where there's a star in the middle, the sun, the big hot glowing orb that keeps us warm. And then around the sun orbit 9 major bodies. So these planets are called Mercury, Venus, Earth, here is us, Mars, Jupiter, Saturn, Uranus, and Neptune. Here's what the sizes of these objects look like to scale. The sun is by far the largest object in the solar system, and it's also the one that has the most mass, the most heft. You can't even see Mercury on this basically. It's this tiny little speck here, and the smaller planets like Earth are barely visible compared to the giant sun. The planets orbit in roughly the same plane. They all seem to be orbiting around in roughly the same direction and roughly without much skew between each other. This is the inner part of the solar system. Here's the sun to scale. Here are the orbits of the 4 inner planets. And if you zoom out, you can see the 4 outer planets as well. And this is the previous size of the image I was showing in the last slide. So we can then ask the question, why is it that the planets move this way? Why do the planets orbit around the sun? Why, in fact, does anything orbit around anything else? And the answer, it turns out, is gravity. So we're, of course, all familiar with gravity. It's what holds us to the ground. When we jump upwards, gravity pulls us back down. And when an apple falls from the tree, it's due to gravity. But when gravity is acting in this way, it's hard to understand how it can also cause something to go around something else. So that's what I'll try to explain here. But first, I'm going to give a little bit of basics about how gravity works. Every two masses in the universe exert a gravitational pull on each other. I have mass and my computer has mass. So we are both pulling on each other and trying to come and collide with each other, essentially. Gravity is pulling us together with myself and the computer. You and I, no matter where you're watching this from, exert a gravitational pull on each other too. And gravity is trying to pull me to collide with you from behind your computer. Every two masses in the universe do this to each other. But it turns out the reason I don't fly towards my computer and my computer doesn't fly towards me, and I don't fly towards you and you don't fly towards me, is because the more mass you have, the stronger the pull of gravity. And put frankly, you and I don't have that much mass, especially since we're nearby something with much more mass, in our case, the Earth. So the Earth's gravitational pull is very, very strong, and that keeps us firmly rooted to the ground and not flying towards each other. So the more mass an object has, the stronger its pull will be. So if you have a big object pulling on a small object, it'll essentially be like the big object feels no pull at all, and the small one just flies towards it. The closer two masses are, the stronger the pull of gravity. So here I'm showing two masses that are the same, mass 1, mass 2, and mass 1, mass 2. But on the top, I've put them further apart from each other. At first, their pull is going to be weaker than the pull of these two. So they're not going to be pulled together as fast or as strongly as they would have been otherwise. And that's why it'll take longer for them to get to each other in this demonstration. So we've shown several examples of how gravity works by pulling on each other. But that doesn't necessarily explain how gravity, which we often observe pulling something into collision with itself, if I drop an apple from my hand, it will fall down and collide with the ground and it won't go into orbit. Why is it that the moon orbits the Earth, for example? Why is it that the Earth orbits the sun? How is it that gravity can give such different results for planets as it does in our everyday experience? And it essentially comes down to the fact that the moon doesn't fall to the Earth and the Earth doesn't fall to the sun because we're going far enough sideways, fast enough sideways to miss. And I'll kind of explain what I mean here. So imagine you've got an apple and you're on Earth and you're very tall and very strong. And you drop this apple, it will essentially go straight down to Earth and crash into Earth. Okay, that's our normal everyday experience. Now, what if instead of dropping this apple, we throw it forward a little bit? The apple will fly forward in a trajectory and it'll eventually fall back down to the ground. Okay, so let's do this again. Let's throw it a little bit harder this time, and it goes a little bit further. Now, let's start throwing this apple even harder and even faster. The harder and faster we throw this apple, the farther it will land before it eventually hits the ground. But what if we can throw this apple so fast that it essentially misses the Earth? It essentially goes all the way around the Earth without ever hitting it. If it does that, then it'll eventually come back to its original position. And that's what happens when the moon orbits Earth. The moon is going so fast sideways that it never crashes into the Earth. Instead, it just constantly escapes missing the Earth. It just is going fast enough on the side that it misses the Earth and never comes into collision with it. Now, it has to be a little bit of a balance though, because if the moon is going too fast sideways, then it'll just fly away. So the moon is falling around the Earth, but going fast enough sideways that it misses. The planets are all falling around the sun and doing exactly the same thing. And that explains why their orbits are going in these circles or in these slightly elongated circles in some cases. They're essentially all falling, and the closer they get to the sun, the more gravity they feel. The more far away they get, the less gravity they feel, and that explains the shapes of their orbits. And this revolution has allowed us to predict the motions of the planets to extremely high precision, essentially making it possible to perfectly predict where the planets are going to be at any given time. And when you absorb this fact that the Earth is not the center of everything, we can realize something as well, which is that the sun, this glowing orb in the sky, is not actually that different from the stars that we see at night, these pinpoints of light that orbit around us. The sun, in fact, is a star just like all of the other ones that we can see. And that fact gives us hope that perhaps all of these other stars may have planetary systems around them.